absolute confidence. You know, if you've ever needed to measure something incredibly small, you already know a standard ruler just doesn't cut it. It's just not precise enough. So today, we're unlocking the secrets of the Vernier Calliper. Think about this for a quick second. How do you accurately measure a fraction of a millimeter? Something like, say, the thickness of a single coin. I mean, sure, if you stack 10 coins together, a standard classroom ruler might help you find the total height of that stack, right? And then you could just divide that number by 10 to get an average. But what if you need to find the exact, precise thickness of just one individual coin? Well, to do that, we need a far superior tool, one designed specifically to measure down to a tiny fraction of a millimeter. So let's break down exactly how this instrument works. First, we'll look at the anatomy of the caliper. Second, the least count formula. Third, the measurement process, and finally, correcting zero errors. Let's get into it.
All right, Section 1. Anatomy of the caliper, beyond the everyday ruler. Now, before calculating any numbers, we really must understand the physical structure of our tool. It kind of looks a bit like a metal wrench, but it's incredibly versatile. It's actually equipped with 3 distinct measuring mechanisms. The large lower jaws, labeled A and B, well, those are your outside jaws. They're absolutely perfect for gripping the outside of a pipe or a coin to measure external diameter or thickness. Then, up at the top, jaws C and D are your inside jaws. These are designed to slip right inside a hollow tube to measure its internal diameter. And finally, that narrow strip extending from the back, that's the tail, and it acts as a depth gauge for capturing the exact depth of a hollow object. But the real magic of this measurement doesn't just happen with the jaws. It happens between 2 interacting scales. So you have a fixed main scale, which looks exactly like a regular ruler with standard 1 millimeter markings. But riding right along that main scale is the vernier scale. This is a sliding strip that is exactly 9 millimeters long. But here is the absolute genius part of the design. Those 9 millimeters are divided into 10 perfectly equal parts.
Moving on to Section 2, the least count formula, unlocking micro precision.
The crucial point here is figuring out the absolute smallest measurement this dynamic duo of scales can accurately read. And this brings us to a really foundational engineering concept called the least count. It's simply the mathematical difference between one division on the main scale and one division on the vernier scale. Basically, it's the gap between the two.
Let's break down the math real quick. We already know one main scale division is exactly 1 millimeter. We also know the vernier scale takes 9 millimeters and divides it by 10, meaning one vernier scale division is 0.9 millimeters. So by subtracting that single vernier division of 0.9 millimeters from the main scale division of 1 millimeter, we achieve an incredible level of measurement precision.
1 millimeters. That means your vernier caliper can confidently and accurately measure lengths down to 1/10 of a single millimeter. I mean, just imagine taking the tiny gap between 2 millimeter lines on a standard ruler and splitting it into 10 equal pieces. That is the exact power you hold with this tool. Pretty amazing, right?
All right, Section 3, the measurement process, your step-by-step masterclass.
Let's see how this all builds into an actual measurement. To take a measurement, you must follow a strict 2-step instruction set. Step 1. Identify the main scale reading. You do this by looking at the 0 mark on the sliding vernier scale and seeing exactly which main scale line is positioned just in front of it or to its left. That is your base main scale reading. Okay, Step 2. Calculate the vernier scale alignment. You're going to scan really closely along the vernier scale to find the single exact marking that perfectly lines up with any line on the main scale above it. It'll form one continuous, perfectly straight vertical line.
And this right here is the golden formula you'll use to combine those 2 steps into your final ultra-precise reading. The total length of your object equals your main scale reading, plus the result of your least count multiplied by your vernier scale reading.
Let's put this into practice so it makes total sense. Imagine you place an object in the jaws. You look at the vernier 0, and it has just passed the 4.3 centimeter mark on the main scale. So, Step 1, your main scale reading is 4.3 centimeters. Next, Step 2, you scan the vernier lines and find that the 4th division is the one that perfectly aligns with a line above it. So you simply calculate the vernier scale alignment by multiplying that 4 by our least count. Now remember, our least count was 0.1 millimeters, but since our main scale is in centimeters for this example, we have to make sure we convert that to 0.01 centimeters to match our units. Always check those units. So we multiply 0.01 by 4.
Adding that calculated 0.04 centimeters from the vernier scale to your 4.3 centimeter main reading,
gives you a highly precise final measurement of 4.34 centimeters. It's actually beautifully simple once you trust the process. Identify the main scale reading, calculate the aligned vernier line, multiply by the least count, and just add them together.
Which brings us to Section 4, correcting zero errors, troubleshooting for perfect accuracy.
Now, before you trust your final measurement completely, you absolutely must ensure your instrument isn't secretly miscalibrated by a common flaw known as a zero error. To test for this, simply fully close the external jaws with nothing inside them. If the zero marking on your main scale and the zero marking on your vernier scale perfectly match up to form a single straight line, great, your tool is perfect. But if they do not exactly coincide, well, you've got an error that must be accounted for mathematically.
There are essentially two types of zero errors, and the fix is beautifully logical. Notice the relationship here. If the zero of the vernier scale rests to the right of the main scale zero, your instrument is basically starting past the starting line. It's showing slightly more than the actual length, so you're overestimating. Your action? Subtract the error from your final reading. Conversely, if the vernier zero rests to the left of the main scale zero, your tool is underestimating. It's showing slightly less than the actual length. So in this case, you must add the error back to your observed reading.
While the right side error is pretty straightforward to calculate. You just find the coinciding line and multiply by the least count. Calculating a left side error involves a uniquely specific process. Let's walk through it. Say you identify a left side zero error. You scan the vernier scale and find that the third division perfectly coincides with a main scale line. Because the scale is shifted left, you must first subtract that coinciding division number from the total divisions, which is 10. So 10 minus 3 equals 7. Then you multiply that 7 by the least count of 0.1 millimeters, giving you a zero error of 0.7 millimeters. Finally, because it's a left side error, you add that 0.7 millimeters back to your final observed reading to get the true, accurate length.
And there you have it. You've now mastered exactly how to identify the main scale reading, calculate the delicate vernier scale alignment, convert your units, and even correct tricky zero errors to guarantee perfect accuracy. The Vernier caliper is literally no longer a mystery.